Hello everybody, welcome to Engineering is Everywhere. My name is Tyler Lay. I'm an Associate Professor of Civil Engineering at Oklahoma State University. Today we're going to talk about two things. We're going to learn about what are materials engineers, and then how do engineers use science in what they do every day. Let's start out, materials engineers. Materials engineers, they either make new materials or they take existing materials and find ways to make them better. They do this with plastics, with glass, with steel, with ceramics, all these things. We're always looking for ways to try to make something better. Materials engineers try to understand materials on a very, very small scale. We call it a microstructure. Micro meaning small, and structure meaning how something is built. Now, in science, we commonly use observation, things we see, and we build these things called hypotheses. We say, we think we understand this, let's test it. We think we understand this, let's test it. We keep changing this and improving it over time. And we use a lot of science in engineering. Now, to make these observations, a materials engineer often has to look at things at a very, very, very small scale. And to do that, we have to use really cool tools. And we use microscopes. Hopefully you've used a microscope, and we're going to be using one today. And this one is called the Cyclops. Not only does it look like a little eyeball, but it is a microscope, and we can look in lots and lots and lots of different things. Now, to understand and kind of a analogy to what I was saying earlier about understanding microstructure, I'm going to start out talking about a picture. I'm going to be starting out talking about a piece of newspaper and a picture. And as you can see in this newspaper, there's a woman with her cat, okay? And that's what your eyes see. But if we take the Cyclops and we look at it, if we look right at the cat, for example, and we go and look at it, that it doesn't really look like a cat on a microscopic scale. It looks like a bunch of dots, okay? A bunch of individual dots. And those individual dots come together to make colors, okay? To make orange, white, all kinds of things like that. So again, these individual micro dots come together and build something larger. They build a structure that we see from the outside. This might, when it comes to materials, this might be able to describe how the material, why it has its strength, why it's able to last a long time, why it's light, all kinds of different reasons. Again, if we can understand how things are built on a microscopic scale, and we can understand more about how they're going to behave. So let's talk about some more materials. Let's talk about Kleenex. A Kleenex, maybe that's something you had in your classroom that you've seen before. If you use the Cyclops to look at the Kleenex at a microscopic scale, you'll see it's a bunch of loose fibers that are somewhat wound together. Okay? Loose fibers, and those fibers are great for catching things that come out of your body. We can look at these fibers as well. These are a little bit more loose. See, and we can see when we hold these up, I wouldn't want to wear a shirt made out of this, right? It wouldn't keep me very warm, and you'd be able to see right through it. But if we come down with another material, a very, very high quality material, and we go and we look at it together, this is like a jacket, a woven jacket. We can see, look how tight that weave is. Now we can't, because that's so tight, and weave means like how interconnected those fibers are. Because they're so tight, we can't see through it. It keeps us warm, okay? And we can make it different colors. There's kind of a tan color. There's a red color, all by changing these fibers. It changes the way it performs. It changes the way it looks. Again, if we can understand things at a microscopic scale, we can understand how they perform at a macro scale or a much, much larger scale. Let's talk about sandpaper. Sandpaper is this rough material. You run your hands over it, and on one side it's smooth, and as you can see, it's like paper that's smooth. There's not a lot of bumps. And on the other side, there's these little sand grains that are actually glued to the surface. That's why it's called sandpaper. They actually glue these little sand grains to the surface. They're like little hills. When they go, and that's why they feel bumpy, and that's why they're able to make things smooth. Those hills run over things over and over and over and over again and break them down, smooth them out, and make them flat. Let's look at cardboard. Now this is cardboard. This is something you've seen before. Hopefully you've seen them in boxes and things like that. If we look at cardboard on a microscopic scale, where you really, really zoom in, I guess I'll hold it over here just so you can see that cardboard in case you didn't get as good a shot. If you zoom in on that cardboard on a microscopic scale, it's actually made of a bunch of individual fibers, okay? But we build these corrugations, these loops, these bumps in it to help give it strength, okay? So cardboard is actually made up of little bitty pieces of paper, little bitty pieces of individual paper that are actually wound together. Another material that's kind of cool that you've probably had experience with is Velcro. If you look at one side of Velcro, the side that's not very hairy, if you look at the other side of Velcro, you'll see that there's actually these individual loops. These individual loops. There's a whole bunch of little bitty loops. And if we look at the other side, the part that is hairy, there's these little things for those little hairs to go through, those individual things to go through. They grab together. They actually poke through there. And it's this adhesion. It's these two things coming together and pulling apart. You hear that noise? That's me pulling those individual pieces out of the loops, pulling right out again and again and again. And that's how Velcro has its strength. Again, if we understand how something works on a microscopic scale, then we can understand how it performs at a macro scale or a much larger scale. So now I'm going to talk about concrete. Again, a material that I really, really like. It's got, as you can see, it's got little bitty holes in the surface. Yeah, it doesn't look like it has holes in it. It looks like it's strong and it's solid. It's got little bitty holes in it. And if we could use a much stronger Cyclops and look down at a much smaller scale, we would find out that concrete actually looks like a sponge. It actually looks like a sponge, and this is what a sponge looks like underneath the Cyclops. Okay? Wow, look at all those holes. So water will actually move through concrete if it sits on it long enough. And it can actually cause problems with the concrete. It can cause it to fall apart, to crack, all kinds of bad things to happen to it. But if we can find a way to close up those pores or to keep them very, very, very tight, those holes, then we can keep the water out, okay? Just like a sponge. Another thing I'm going to talk about is foam. Now foam, that's this really thin, light stuff that we use to pack things, right? Maybe it's in your gym has some foam in it, or other things have foam in it as well. If we look at that foam, it's so light. On a microscopic scale, it's actually made of a bunch of little bubbles. A bunch of little bubbles that are hooked together with little plastic in between. That's how a foam works, and that's why a foam is so light. That's why we say the density is so low. The weight per volume ratio, or the fraction, is really low. Look how light it is. The final material I'm going to talk about today is wood. And wood is actually a very complicated material. It's a material that comes from trees, right? It comes from trees. And it's it's a natural material, but it's very, very complicated. If we were able to use the Cyclops and look on it on different levels, it looks different depending on how you look at it. Looks different. So those are the sides of the wood that I was just showing you. Those are the sides, okay? And this is the top. Whoa, what's that? Like little holes. That looks, I observe, that looks like little holes. Well, I wonder if they're on the other side. I flip it over and I look at it on the other side. Oh, I see the same holes on both sides. That's real interesting. And there's other things we can do with wood. You'll actually find wood has different strengths depending on how you load it. For example, if I take this wood and I try to push on it, I don't break it. But if I take this wood, which looks the same, it looks exactly the same, but do you see the grain's different? See how the orientation is different on the top? See how the lines look different than they do here? That's a clue. That's an observation I can make. That if I go and load it like this, actually I don't even need to push it. I can bend it really easily. Really, really easily. I can just break it. Wow. What's going on? Well, let's use the Cyclops. Let's actually look at it. Well, if I look at it like this, I see these individual things, and then if I look at it like this, I see some of the straws, I see some of the holes, I see some of these things, these holes, and I see them on both sides. So it looks like that this piece of wood was made up of these holes on the top and holes on the bottom, and it looks like they go through. It looks like when I look on this side, it's just the side of the straws. It's just the side of the straws. But if I look at this piece of wood, it's different. It looks different. It looks very different. And if I start to look for those straws, they're not on this face. This looks more like the side. And here I see the holes again. So it looks like this piece of wood has those holes on the top and holes on the bottom. It looks like they almost like they're straws that run through this wood. Well, if that was the case, then I should be able to take this wood in a straw. If I blow through it, air goes through it. Let's try it. If I have some water, it's just normal water, and I have the piece of wood, and I actually put inside, and if I blow through it, something should come out, right? I should make bubbles. It works. It works. There's holes on the top. There's the sides of these things. It's like there's a straw going through the wood. And that's right. That's actually how trees work. If we go and we look at a tree and we look at how it grows and how it has to work, is they're in the ground where the roots are. It has to pull water up through the trunk of the tree out to the leaves. Okay? And if we actually took a cross section, remember that's a cut. That's like a 2D cut, like a flat cut through the material, and I looked at it, and I looked down it, I'd actually see, it'd actually be like I was looking at a bunch of straws looking at me. It almost looked like this. This is like a tree. The leaves are up here, the roots are down here, and these are those straws going up, just like this. Just like this. And so when those straws are on their side, like in this case, here and here, if I want to bend this, I can't. It won't break. It's super strong. Look at those straws. They're strong too. But if I change those straws, and they're like this, I'm going to use just the same thing, it's just a little bit larger, and I go to bend it. Look how easy it is to bend that. See, this is understanding the microstructure and how it impacts the macro performance of the material. So that's why when I bend this, these straws are going up and down, just like this. It's easy to break. If I had tried to do that with this one, straws are like this. I can bend it all I want. Won't break. So, what do? We made observations. We learned from those observations. We made hypotheses. We tested those hypotheses for materials. We found out ways that, you know what, if I want to make wood, if I want to make some wood for my house, I probably want it oriented like this. I probably want it cut and oriented just like this. This will make it strong for wherever I live. That if I cut it like this, it's going to be weak. And again, when I go and I load it, it's going to break really easily. Now, I want you to try this on your own. I want you to take the Cyclops. I want you to, again, go on a scavenger hunt, find some interesting materials, bring them back, look at them, try to understand the microstructure of those materials, and help use those observations, use that science to make hypotheses about how those materials work, why they're a certain color, why they have strength on a more macro scale. and you'll be a materials engineer. Thank you so much. Take care.